And the backup recording.
Well, at the time, we did not have any of it.
Sorry, you were saying, Alberto?
Yeah, at the time, we didn't have any of it. People were asking for recordings and never managed to get them. So I'm kicked out from the screen sharing now that activated the recording.
Oh, yeah, but we can still see the slides.
But I can't move them.
Oh.
Let me try again. Where was it? Yeah. Oh, cool. Okay, now I have them.
Okay, perfect. Yeah, and we can see them. And the live stream is also live. So then I would say let's get started. Yeah, welcome everyone to the UCL InfoSec Research Seminar. It's great that you're all here. So this is one of our first sessions in the new academic year. And it's my particular great pleasure to introduce Alberto Sonnino, who is a researcher at Miston Labs, and where he's working on research in distributed systems, scalability in distributed systems, and so forth. And it's particularly great because, like, Alberto has also been a former UCL PhD student, right? And has now moved on to do great work in industry. And today he brought some research that they published like a year ago or so, I guess, which is actually used in production. And I'm really looking forward to see this presentation. Yeah, so take it away, Alberto. The stage is yours.
Thanks. So this is actually about two papers, as Philip said. Narwhal is one paper, Eurosys last year or the year before, and then Bullshark, which is CCS last year. So they're put together into a single presentation because kind of one builds on top of the other. And what's maybe a bit particular about those papers is that these two systems that I'm going to present both run today in production as part of what is now called the SUI blockchain. So, you know, if it doesn't work, if you find issues during my presentation, it will have a pretty big impact. So, classic settings, Byzantine fault tolerance. So I'm starting with a very quick intro, but if you raise your hand, I will know that you would like more intro, and then I can make it longer, okay? So what happens is we have a variety of nodes, right? We elect them through a variety of mechanisms, right? In our case, we use proof of stake, but it doesn't matter for this presentation. What happens is that we have some participants, each own a computer. This computer will run the software that we give them, and up to a third of them can be malicious. Not just crash, not just unavailable, completely bad. They can even run a different software, they can tweak our software, they can leak their keys, they can do whatever they want to try to mess with the system, right? But still, we would like to make it work. So as long as we have more than 2/3 honest participants, the protocol should keep doing what it should do. So what should it do? Well, it's a classic blockchain core, right? So we have a user who creates a transaction, a statement, it signs such statement, and sends it to all the nodes, right? This is what it's called submitting a transactions in common terms. Then what will happen is that this variety of nodes will run what is called a consensus protocol, chat with each other, and at the end of the day, they will all agree to, after verifying the transaction, that it should be sequenced. So it receives an order with respect to all other transactions of all other clients. And this should happen despite the presence of bad nodes, the red crossed node that you see there. At the end of the day, once everybody agrees on a sequence of transactions, the transaction is executed and persisted forever through a chain of block, hence the name blockchain. So to make it a little bit more concrete, but that's just the introduction, right? This is like the best examples that basically gives us a living, right? You can send money with that thing. Bob creates 5 coins, a statement that says, well, I'm going to send 5 coins from my account. Well, actually, Alice creates the statement to send it to Bob. She signs, send 5 coins to Bob. She sends such transaction to the system of nodes. It gets sequenced. So now we have a total order of multiple transactions that Alice sent or that someone else sent, all ordered, right? Intuitively, this will prevent double spending in case Alice is sending the same she's spending more than what she owns, basically, right? Only the first order transaction will be executed. After verifying the transactions, the transfer will happen and the transaction will be executed forever. So here, this whole system, this whole discussion is about how do we order those transactions? Turns out it's a pretty complicated problem. People have been trying to do it for like 30 years. They succeeded in a variety of ways, with a variety of performance and in a variety of settings. So is that clear what we're trying to achieve until now? Yeah, no hands raised, so I go, right? This is just a brief introduction. If you know a little bit what blockchains are, you wouldn't need any of it, right? Anyway, here it's just about the sequencing core. So what we would like to do is that to have a consensus message, so a consensus protocol that runs with 0 message overhead with respect to the data dissemination layer, right? Those messages need to be gossiped or sent from one node to another so that everybody eventually knows, right? We would like to avoid something which is called a view change in our system. So if you do not know what a view change is, you're a lucky person because you won't need any of it through these newer family of protocols, right? If you know what it is, it means that you spend quality time studying BFT, HotStuff, who all are very complex and error-prone view change mechanisms. Then no common coin and other complicated things, at least until a few months, years ago, very hard to build it. I don't think, actually, I'm quite sure there are no blockchain in production that use a common coin for the sake of consensus as of today. They may use common coins for applications layers, but this tells you that they're quite hard to build and extremely hard to build if you want them performance, basically. So we want it simple, no view change, no common coin for those reasons, right? And so, well, for those who are a little bit more into distributed systems, we wanted to exploit periods of synchrony of the network. So the network sometimes is good. Sometimes all the messages are sent extremely fast from one node to another. Well, we should try to not wait too much and take advantage of network reliability periods while being extremely robust once the network is not reliable anymore. So what happens to all the consensus cores so far, right? Well, most of them, only with a few exceptions, right? They are usually very monolithic, right? They start by having a transaction sharing mechanism, which is part of the consensus protocol. And sometimes they also have a data dissemination layer to help out strugglers node, which then does a little bit of replication. Sometimes this little bit becomes like 2x replications on the data dissemination layer. And so another thing that happens, which was quite surprising, is that 30 years of literature has been focusing on improving the communication complexity of such consensus protocols to best that can be achieved linear. And it turns out that actually communication complexity does not really matter for the sake of consensus. Sure, if you become crazy and you go like cube and more than that, it may become an issue, but going up to quadratic is not a big deal, as we'll see on later on this presentation, right? And of course, no view change, right? View change are really the thing that makes those protocols very hard to build and extremely error prone. So here is how most of the typical consensus core work, right? Not our own, but from PBFT back in like 99 to HotStuff in 2019, they kind of follow a similar pattern, right? You would have one of the nodes, so one of these parties that broadcasts proposal message for ordering, gather votes into a certificate, and rebroadcast it back. One way or another, depending on the protocol, after one, well, actually 2, 3, or even more of these hubs, you will start sequencing and agreeing on what block has been seen by everybody else before which other block, right? So as you can see, this is actually a problem. So communication complexity may be linear, but you will realize that the resource utilization of your machine is very suboptimal. You will have one node called leader that will use a lot of CPU, a lot of storage, and a lot of bandwidth, while basically all other nodes will be there chilling. They would just receive some messages, verify them, and reply with short statements called votes about correct messages, right? They do not use the resource at all, right? But that leader, every couple of seconds, sometimes every couple of hundreds of milliseconds, rotates, which means you need to over-provision all the machines you have for the event where they become leaders. Well, we have 100 machines, 100 over-provisioned machines just for the sake of one leader seems quite bad. And another thing which makes things even worse is that this type of protocols works by using sequentially the resources it has. So it will start by using a lot of CPU to compute a block, compute its hash, various cryptographic proofs within it. Then CPU is not needed anymore. We're going to use storage to persist it. So I/O is bottlenecking. After that, once everything is stored, we can ship it. And so the leader needs to multicast the message to everybody else. Then bandwidth becomes a bottleneck, while CPU and I/O is virtually unused. So these are like key performance issues that we had like back in the days when we started building those things in production rather than leaving them as academic prototypes. Then there is another issue related to this famous view change. Basically, when you have a faulty leader, what happens is that you don't only lose all the work that is done by the faulty leader itself, but also by the previous leader and potentially even the leader before, depending on the protocol. So what usually happens is that one faulty leader can kill the work and waste the work of a variety of previous leaders. And this is by running, again, a complex view change mechanism, which is extremely slow. Usually it will cost you like 20, 30 seconds of no activity on your system. So what do we do about it? Well, we start with a DAG-based Mempool, which we call Narwhal. And this is a data dissemination layer that is going to ship your data in a special way. That special way will help later a consensus core to take advantage of the structure of such data in order to interpret a consensus protocol out of thin air, basically, without extra protocol messages. So yeah, at the end of the day, what we realize is that building such mempool, such data dissemination layer, is actually the bulk of the work. This takes a lot of engineering efforts. The prototype of the mempool took 3 of us about a year to get it up and working, right? Well, plus another year to put it in production. So the first year was only for the prototype, right? And then once you have that thing, the consensus core is very simple. So it can run in like 100, 200 lines of codes and everything follows out of it. So here is the structure. It's not that complicated, right? I mean, once you get it right, everything looks easy. So what you do is that we have one validator. We call it the Narwhal mempool, the big box there. So that's one of these parties, right? And it runs a variety of processes. Let's call them processes for now, right? One of those processes is special. We call it the primary. You can see it on the slide. And N of others, basically all the others, are called workers. So now, upon accepting client transactions, what will happen, through whatever load balancing mechanism, the transaction goes through the workers. And now, every worker will pairwise communicate its transactions to the workers of the other nodes. So what does it mean? They assemble those transactions into batches, usually 0.5 megabyte, something like that. And you will have worker 1 of validator A sending its batch exclusively to worker 1 of validator B, worker 1 validator C, and so on and so forth, right? Worker 2 communicate only with workers 2 of all other nodes, worker N only with worker N of all other nodes. So they ship those batches and they do one extra thing. They keep a rolling hash of those batches and give them to the primary. The primary is that special process, which is quite lightweight. It only receives digests from its own workers. And what does it do with that? it runs what we call the Mempool protocol. And now it's all about the Mempool protocol in the upcoming slide. So this architecture, if you already look at it, breaks the sequential use of resources. You will have a variety of workers who need to use CPU, storage, and bandwidth, sure, sequentially if you look at them individually, but if you have a variety of workers that run on the same machine, that do not start exactly the same time, do not work exactly in lockstep, you will, on overall, have a sequential use of resources. A parallel use of all your resources. So the Mempool protocol. So what do you do with it? The primary collects all the digests that it has, and it puts them into a data structure that we call a block header, right? So block contains metadata, sure, and then a collection of digests that comes from the hashes of the batches of its worker. So a header will contain 2f+1 links to the previous blocks. We'll see that in a bit. And now we do something which is quite familiar for those who have been looking at those protocols for a while. You take the header and you disseminate it to all other authorities. Then all other authorities look at it. If it's the same header that comes from, if it's the first header for a given round number that comes from one authority, they vote for it. For now, let's say if the header is correct regarding some uniqueness properties, we just vote for it and send back a vote to the originator, to the sender. The sender collects a quorum, 2f+1 of those votes, aggregates them into a certificate, and sends back the certificate to all other nodes. So now remember, every time that you have a header, it links back to a quorum of certificates of the previous round. So this structure is what we call a round, right? So this is a single round that happened to here. And if you're a little bit into distributed computing, you can realize that this is an instance of Byzantine reliable broadcast, provided that we have, well, the 2f+1 links, right? And that there is a background synchronizer to sync out of band whatever blocks may have been missed by some authorities, right? So what do we do with that? We run one round and we run multiple rounds, and every authority, so every node, runs such protocol in parallel. So at the end of the day, what you will have as the view of a single validator is a DAG, right? Every validator may have a partial DAG, right? Each DAG will be a subset, one of the other, but eventually they will start looking the same, at least for the parts of the DAG that matter. So every DAG here is a DAG made of certified header. It's not a DAG of headers, right? So there are no equivocations. There cannot be two different DAG vertices created by the same validator for the same round number, here numbered from 1 to 5, right? And so this is actually the goal of building the Mempool. It builds this structured certified DAG that advances round by round, producing parallel by all validators. So since you're quite late, I'm going to skip the next session, the next set of slides. The next set of slides are about how you use such protocol in order to build on top of it any consensus protocol. You can take whatever protocol you have, BFT, HotStuff, to name a few, and you can run them on top of the Narwhal Mempool. I'll go directly on the next set of slides, which will say, well, now that you have such Mempool, how can you interpret a consensus protocol out of it? Basically, how can I look at such DAG from a node perspective and linearize it in a way that I only have a sequence of blocks and that every validator agrees on the same sequence of blocks? Remember, every validator may have only a partial view of that DAG, right? And so the consensus protocol will be called Bullshark. Let me go there. Yeah, this will be the Bullshark protocol. So first thing that we do, we slightly modify the DAG to have timeouts. It doesn't really matter, unless you're looking into proving the liveness of those systems. But basically what you do is every time you're on an even round and you're about to change your round number to create a new block, you would wait to receive a predefined leader. But we'll come to that later. So about the Bullshark protocol. It's a zero-message, partially synchronous consensus protocol. So if you look at the Bullshark paper, you will actually see that there is also a fallback in asynchrony, but we can forget about it for now. I'll just explain the simple version because it turns out that the simple version is all you need, is the one we run in production, and the fallback sure may help, but it's actually quite complicated. So how does it work? We have a DAG that is being built, right? And we want to output a linearized sequence of blocks. So we just need to interpret the DAG. No extra protocol messages, nothing at all. So let's say that we build the DAG up to round 2. That is the view of a node, right? Time goes to the right, and every line is a block authored by a validator. We only have 4 in this example. So first thing we do is we say every even round, deterministically, we select one of our validators and we call it leader. So here we see L1 is the leader, right? So we can just use round robin so that every node gets its chance to become a leader every so often, or we can have smarter strategies that go to future work. Okay, so what do we do with that, right? We have a leader, and now we will use it as anchor to linearize its sub-DAG. And how can we do that in a way that every honest validator agrees on the anchor and so ends up having the same linearized sequence of blocks? So here's the rule. The first rule is the leader needs to have f+1 links from round R. Basically, leader here in this example is at round R2. It will need to have f+1 children at round 3. So f+1 block certificates at round 3 should link back to the leader. If that happens, we will commit it. So here we see that the first block, the one that we see at round 3 here, does not link to the leader, so it doesn't count. So we have another one here, another certificate, and that is one support. The red line here, you see that this second certificate is actually linking to the leader. So that's 1. f+1 in this particular example equals 2, because we have only 4 nodes. Then we have the other 2 blocks, the DAG keeps building, and we realize that we do not have enough support. So here, typically, once a leader lacks supports in consensus protocols, you need to trigger a view change. A particularity of Bullshark is that you do not. You only need to ignore, you don't commit L1, and you keep building the DAG as if nothing happened. Eventually reach round 4. It's an even round, so we can elect another leader, again, deterministically. The next one using round robin would be L2. And now we keep building the DAG again. We need to wait for round 5 to know if L2 has enough support. We see here round 5, it's a happy round. We have f+1 links from certificates at round 5 toward the leader. Those are the blue links that you see on the screen. And now we can apply the commit rule. It's actually not that complicated. This is like the main commit rule to remember. So upon finding an anchor that you can commit, L2, we check if there is a link between L2 to L1. So if there is a path through the DAG between those 2 leaders. In that case, there is. You can see the red lines are linking through a white certificate, leader L2 to leader L1. So if that happens, we first go back and commit L1 and then commit L2. So in practice, we recursively go as far back as we can by following the links through the DAG to first commit the earliest possible leader that we did not commit before, and then advance and commit the next. So what does it mean now, committing L1? Well, committing L1 means that you actually commit all the sub-DAG of L1. So remember, every sub-DAG here is a certificate. Every certificate has been created by a different node, and every certificate contains a variety of digests linking to a lot of different batches of transactions. So if each of these certificates contains 5, 10 to 100 hashes of half a megabyte of transactions, basically, you can really commit a lot of transactions upon deciding to commit a leader. So here, you take all the green part here, and these are all the blocks that you can deterministically linearized. Whatever depth first search will work. You can even order them by gaseous, alphabetically, it doesn't matter. We just need to know that L1 is committed and all its sub-DAG is committed as well. And once this is done, we can go and commit L2 as long as the entire sub-DAG of L2 except the sub-DAG of L1 because we already committed that. So you see that every time we manage to commit anything, even if we miss the leader L1, while in other systems we would have wasted the payload carried by L1, in this case we don't, simply because by the links from L1 to L2, or simply because some of the blocks, even L1 is a parent of L2, by committing the entire sub-DAG of L2, we will end up committing a lot of blocks at once. So this is about the protocol, and now this is how the implementation works, right? So at the high level, it's Rust, uses pure TCP, nothing else. RocksDB as storage, and Dalek as a cryptographic library. So you put it geo-distributed. That is actually the good way of benchmarking distributed systems, but it's also the most expensive way. So if you reproduce experiments, be very careful, right? In terms of machines at night, we learned that the hard way. And these are the performance that you get. So forget about the Tusk, the green line. We did not have time to talk about that today. There are other talks on YouTube about Tusk exclusively, if you like, but just look at HotStuff, which is the state-of-the-art that was there before such protocols, and then look at the blue line, the Bullshark line. So you see that with 15 nodes, so only the dotted line, you would have HotStuff reaching 30K transactions per second. And with the same parameter, same machines and same setting, you would have Bullshark going through 100K, right? 130K, right? So the latency also remains around 2 seconds. 2 seconds is a very good number. And this is the setting where every node is honest. Nothing goes bad, and the network is good. And this is what happens if you have 1 or 3 out of 10 faulty nodes. So in this example, they're just dead. They don't reply. So when they're elected as a leader, well, there is a miss. And you see that here is the core problem we had for a very long time, basically. Upon having unreliable parties, the orange line, HotStuff, would give you very bad performance. You can see that the throughput goes to a few hundreds transactions per second, and the latency, well, we're 30 seconds between committing every transaction, right? This is not the payment systems of your dream, let's say, right? And the blue line goes further than that. Basically, since every time you miss a leader, you don't miss its block. And upon committing a block, a certificate eventually, you would commit most of its transactions recursively or through the sub-DAG commit strategy. You see that, sure, we lose a bit of performance, but we don't lose too much. Latency goes up because we miss leaders, but it doesn't go up to 30 seconds. Now it means we need to wait 4 to 5 seconds before committing a transaction. So this was the main set of slides that I have, but now we can do 2 things. If you're tired, we can stop here and go for questions. If you like, I have a couple of slides that tells you the biggest engineering mistakes that we've made when building those into production that basically required us an entire year from going from prototype to production-ready implementation. What would you like to do?
I think hearing about the engineering mistakes would be great.
Yeah, cool.
Definitely agree.
So, yeah, cool. So those are the main lessons learned. So if we had to do it again, actually, if we had to run any consensus system again, that's the thing we would not do, basically, right? So that's the overview, and we can go through them. They may seem easy, but actually they were not obvious at the time. So the first thing that happened is that we did not implement crash recovery within the academic prototype, nor view synchronization or epoch changes. So what does it mean? Usually, we say in the theory of distributed system that a node is either honest and always following the protocol, or crash, dead, malicious, and then it never follows the protocol. That's not how it works in real life. Basically, nodes need to update, and so they're taken down, and then they reboot, or maybe they crash because they have disk failures, and then eventually they reboot again. And handling those cases is extremely complicated. You cannot consider them bad, blacklist them, or stop listening to them, because this will happen to too many nodes. But yet, if you do it without being extremely careful, what will happen is that you may have equivocations. Good nodes forgetting the message that they sent right before crashing, then rebooting without memory, or by remembering the wrong things and creating bad messages, and so they would look like bad and faulty nodes, right? So we did not build that in the implementation, in the prototype, and that was a big mistake. So collecting the minimum amount of states that needs to be persisted across crash recoveries is actually quite hard. You really need to engineer your code base for that from the beginning. It's not hard if you look at the theory. You would realize that, sure, every time you sign something, you persisted before sending it, but your software is multi-threaded, and it's not clear when the signal should be sent. Basically, the other thing is it's very costly to wait on I/O before going for networking. So having a nice pipeline there took a lot of time. The second thing is actually quite surprising. It's about the synchronizer. The synchronizer is a component that runs in the background, and if you realize that there is a node that is lagging behind, it will need to catch up. It will go collect a history of missing messages and replay them for that particular node. Well, synchronizer, through the 30 years of literature of distributed systems and Byzantine fault-tolerance consensus, have always been considered an implementation detail. And it turns out it's actually the main bottleneck of all these systems. You don't see them because when you run traditional benchmarks, you never do a crash recovery experiments, and you never do an experiment where some of the nodes lose connectivity for 1, 2 to 10 minutes, and then go back and need to be up to speed again, right? And if you do that, you realize that you eat all your CPU time for verifying old signatures, and you're basically DDoSing your own nodes if you're not careful. So we had a basic synchronizer only to satisfy the basic liveness properties of the system. And then we went through, well, we applied the literature by saying, well, it's an implementation detail, right? We took like two people and said, well, build it, right? Big mistake. We should have designed it from the beginning. It has been the main bottleneck for about 6 months in the entire system. It even delayed launching one of the test nets because of. And then epoch changes. You don't keep the same set of validators forever. So you would need to change them eventually. Actually, you would need to change them potentially every day. And there is no real literature about how you do these kind of things. You usually run for an entire epoch. You benchmark with the same set of validators. You submit your paper and call it a day. Well, epoch changes are complicated. And the best way we found, after trying a variety of ways, is you kill your entire system and you reboot it for the new epoch with new parameters. It actually works better. And if you do that every day, you would introduce 5 to 10 seconds overheads once every day on the transaction latency. And it's not a big deal if you do it that way. If you do it other ways by trying to live reconfigure the system, well, it didn't work, basically. We had to scrap down all that code. Then not benchmarking from day one, right? This is strangely a thing that we did for the prototype. We usually do it for papers. We start benchmarking every time that we have while building the prototype, especially if the paper is claiming performance. But we did not do it in the production settings. It was clearly a mistake, right? What happens is people have been like updating the libraries, building the components that were missing, adding whatever monitoring tools that were there. And without realizing that while doing so, they were actually adding a variety of heavy operations on the critical path. And by doing that, well, a lot of concurrency bug happened. And only when we benchmarked in the real internet, so real network variants, and under high load, we started seeing all those issues, like weird congestions that would not work. and spent months fixing those. So these could have been spread through from the beginning of time, rather than having something that looked like it worked. People were all happy about it, and then when throwing load at it, it wouldn't, or would be very slow. And then we have the starting with fancy crypto, right? If you have a crypto team, you will realize that they do crypto, and they do a lot of crypto, and they will start having the latest fancy crypto that they can think of on your system, right? Well, actually, a huge crypto is very expensive, and also crypto agility is very expensive to maintain. What happens is you have very few people who understand both crypto and distributed systems. And if you give most of those people a magic crypto library with a variety of functions, and you tell them, well, sure, every time you kind of need to assign, here is like a tutorial on how to do it, you never get it wrong. And even if we got it wrong, even if we got it right, it was extremely underperformant. So it took a variety of ways to fix it. And the reason behind that was the edge between the crypto libraries and the systems aspects, and namely serialization. So what happened is, every time you sign a message, you need to serialize it, right? The crypto library will provide you a way to serialize your signatures. That's usually fine. Again, not all crypto libraries do, which is already quite a thing. But those who do, they will provide the most simple and naive serialization mechanism you have. That's usually extremely bad. What we do in distributed systems is we often have to receive messages from network, from storage, put them back to network, or put them back to storage. So we always keep a serialized copy of the message in memory, and then we reuse that same serialized copy in order to persist it or ship it through the network and operate on the deserialized copy of the message that eventually we just drop, right? We don't reserialize it. Well, this bad interface with crypto libraries that required special serialization functions created a variety of problems through complexity and huge bottlenecks. And the last was a complex network system. So we had special network engineers that were there and wrote a very complicated network stack based on HTTP, HTTP2, whatnot, right? And these created a variety of issues. So crash recovery became even harder because it wasn't now trivial how to restart these connections and which connection could be dropped without blocking the entire system, and how you would then maintain them alive, because you may have different messages of different sizes, which may need to be optimized in different ways. And finally, those are the two last. So in papers, from the beginning of our papers, actually, what people do is that they isolate the modules through a variety of abstractions, right? If you read the most well-written papers, you will realize, well, you have a component that makes proposals. You have a component that is a synchronizer, a component that is responsible for the safety, that checks the signatures, check the protocol messages, and then other components will do other things. So this is fine, right? This is a good strategy for building proofs. This is a good strategy for writing the paper and explaining the protocol, but this is absolutely not an implementation strategy. If you start by implementing the modules one after the other, you realize that the interface between them is really not like those in the papers. In fact, those modules may run on one or multiple threads. Each module may require to share its thread with other parts of the module. And so they may require to access data extremely fast. And those cannot be easily shared across tasks or across threads if you want an efficient system most of the time. So basically, taking some time and doing some software engineering after you understood the nice system is usually the way to go, rather than taking the module one by one, assigning them to different groups and different teams, and then hoping to glue them together once everybody wrote its own interface. So those are the biggest mistakes that we made and that we would not do if we run more blockchains in life. One never knows. That's it, actually. I mean, I obviously have more slides, but I think that's a good time to stop.
Yeah, thanks a lot, Alberto. This was really like a very, very nice and interesting talk, and also the engineering lessons were super insightful because you usually don't hear about them in that clarity, right? So let me stop the recording and the live stream, and then we can go over to the Q&A session.